Welcome to our lecture video in hydraulics with the topic Hydrodynamics, forces developed by moving fluids. And in this video, we will focus on forces acting on curved plates. And we will also answer 4 sample problems from this handout. Now, under the forces acting on curved plates, we have two cases here. The first one is not in motion, or the velocity of the vane is, the velocity of the vane v prime is equal to 0 meter per second. And the second case is when the vane is in motion. So there is a velocity for the vane or the plate. So here in the first case, when the vane or the plate is not in motion, so we can see here that the initial velocity v1 is equal to the final velocity v2. Now, having this formula for the force, the F here is the force in Newton, that is the force of the jet. So, force of the jet that is acting on the, or that is moving, or that is against the vane. So, F here is the force of the jet. Now, the components of the force Fx and Fy, we have the following formulas. For f of x, the x component for force, we have here the density of the fluid multiplied with the Q, or the discharge by the fluid. And then, we multiply it with the x component of the initial velocity minus the x component of the final velocity. We can get the x and y component for the velocities by the angle here. So the angle of bend of the plate or the vane. Now for the f of x, the other formula there will be q, and then the unit weight multiplied with the unit weight of the liquid divided by the acceleration of gravity times the x component of initial velocity minus the x component of the final velocity. Now as for f of y, that is equal to density of the fluid times the q times the y component of the initial velocity and the y component of the final velocity. And another formula for Fy is equal to Q gamma over G times V1y minus V2y. Now as for the force, that is equal to the square root of the x component, or the square of the x component of the force plus the square of the y component of the force. And then we have here the R. This R here represents the resisting forces, being this Rx here is the x component of the resisting force, and the Ry here is the y component of the resisting force. Let's go to the case number 2, when the plate or the vane is in motion. So this bended plate here or vane is in motion. Therefore, we cannot assume that V1 here is equal to V2. So there will be a different value for the final velocity. So this V2 here is described as the absolute velocity of the jet as it leaves the vane. So how do we determine that? So if V1 here, so V1 is not equal to V2. And then V1 is our absolute velocity of the jet before it enters the vane, or that is the initial velocity of the jet. And then the V2 is the absolute velocity of the jet as it leaves the vane. We can get the value for the U. First, we will get the value of U if the initial velocity and the velocity of the vane is given. So having this formula here, u is the relative velocity of the jet. So relative velocity of the jet, u, is equal to the initial velocity minus the velocity of the vane. And then take note also that since there is the presence of the velocity of the vane here, there will be the different formula for q. Now here in the plate that is not moving, obviously our q here is simply the area and then v sub 1 if it is given. So this is the simple formula for q. Now as for the q here in the second case, so this is the area or the actual area of the jet multiplied with the relative velocity of the jet. So we still need to solve for the value of u. Now it helps also to draw this so it also helps to draw this relationship here of the v2 v1 v2 v sub 2, the u and the v prime, being the u here is the inclined relative velocity of the jet that is given the angle theta of the curvature of the vane, and then we have here the value for v prime, that is the velocity of the vane, and then this is the v sub 2, wherein it does not represent the angle of the inclination. So remember that the angle here, the angle of curvature or inclination of this vane, theta, pertains to the u. So we form here a parallelogram. So since this is a parallelogram of force, so the u here is same value as the u in this point. So it is also equal here. So we get now the value for v2x. So v2x is equal to the v prime plus the u sub x, that is the u cosine. So u sub x here is actually u cosine theta. How about the v2y? The v2y here, or the vertical component of v2, is equal to the, so that is the same with the y component of the u. So that means uy here is equal to v2y that is equal to u that is u sine theta. Okay. And take note also of the sign here. We will base our sign convention on the flow of the jet. So if we assign here for the force of the jet, if we assign here the Fy downward as positive and Fx to the right as positive, therefore the upward direction of the V2y signifies that it is in a negative direction. Whereas our V2x here, since it's the same direction as the Fx, we will get that as positive. That's why in our formula here, as for the V2y, that is actually equal to negative quantity negative V2y. And thus becomes positive on this one. And that will be explained later in the examples. So here for the f of x, so it's the same with the first case, but the only difference is that the q prime is AU. And also, as observed, the value of B1x and B2x and the By and B2y, because we will be using this convention here. Okay, so we have here the 4 examples. Let's solve them one by one. For the first one, so a horizontal jet of water flowing freely in the atmosphere is deflected through an angle of 90 degrees by a fixed curved vane. If the water jet has a diameter of 40 mm and a velocity of 8 meters per second, what is the force required to hold the vane in place? So we have a vane that is curved or deflected through an angle of 90 degrees and it's pointing upward. So that means our vane in 90 degrees will look like this. So it's deflected upward. That's why the water will also be deflected 90 degrees. So our drawing will be like that. So the water has been deflected 90 degrees. Given the water jet has a diameter of 40 mm, so 40 mm diameter, and the velocity of 8 meters per second. So there is V1 here of 40. So V1 equals 80. So 8 meter per second. So V1 is 8 meter per second. And since this is a fixed curve vane of B prime equals 0, so our V2, which is directed upward 90 degrees, this is similar with V1, and that is 8 meter per second. So what is required here? Find the force required to hold the vane in place. That means we're looking for the resisting force R. So we're looking for the resisting force R here. So this is our resisting force R, and we have our X and Y component in order to get the value for the R. So this is Rx, because the water is going in the direction to the left. So this is also our force for the jet or the water. So F of X. Same magnitude but different in direction. Then this is our Ry. So this is also our F sub y. This is our R, the resisting force, and this is F, the force of the jet. So what's our formula for Fx? We will be using the case number 1. So F of x is equal to the rho. So we have two formulas there, so we can use either one of them. Rho gamma B1x minus B2x. So we need to find the value of Q. Now Q is equal to area times velocity. That is equal to pi over 4 times the diameter 0.04 squared, and the velocity here is 8 meters per second. So what is our Q? So shift pi over 4 times 0.04 squared times 8, 0.01. So 0.01 cubic meter per second. So we can now have our f of x is equal to, the density of water is 1000, q is 0.01, and then we have v1x being the 8 meter per second, and v2x. Do we have v2x here? None. There is no x component for the v2. So that is equal to 0. So what is now the value for f of x? So 1000 times 0.01 times 8, and that is equal to 80 Newton, positive 80 Newton. So since it is positive, therefore the assumption that f of x to the left or to the right is correct. Now what we're looking for here is the force required to hold the vane in place. Therefore, what we're actually looking here is the resisting force, that is the Rx. Same magnitude but different in direction. So this is the Rx. Next, we need to find the Ry in order to get the value of R. Now, formula for Fy is equal to rho gamma V1y minus V2y. So, density here is 1000 times 0.01 for the Q. V1y, do we have y component for V1? None. So that is equal to 0. How about V2? What is V2y? V2y is 8 meter per second, but it's directed upward. Now, our sign convention here is downward positive. So, since V2 is upward, we will put here quantity negative 8. So, our value here becomes, so 1000, same value. That will be 80 Newton. So, that is Fy. So, since it is positive, therefore, our downward positive is correct. And since we're looking for the resisting force, this is Ry, that is 80 Newton, and the direction of Ry is upward. Therefore, we can now find the value for R. So, what is the force? It says there, so we're looking for the resultant of the resisting force here, this R. So, Rx is 80 squared plus Ry is 80 squared. So, R is now equal to square root of 80 squared plus 80 squared. So 113.14 Newton. So that is the resisting force. So that's number 1. Now let's go to example number 2. A jet having a diameter of 50 millimeters and a velocity of 15 meters per second is deflected by a vane which is curved through an angle of 60 degrees and which is moving with a velocity of 6 meters per second in the same direction as the jet. So what's this? What is this 6 meters per second here? Well, it says here it moves in the same direction as the jet, and that means it is the velocity of the vane. Determine the x and y components of the force exerted by the jet and its direction and velocity as it leaves the vane. So first, what's the vane here? It's deflected by a vane which is curved through an angle of 60 degrees. So our vane is 60 degrees. Say this is our 60 degree vane. So it will be deflected like this. So I will sketch it. So that is 60 degrees. And then our water here will be deflected also 60 degrees. Now for a much nicer drawing will be here. So this is our 60-degree vein. Oops. So it could be like this. Let's have some small corrections here. There. The important thing there is it's represented by the 60-degree curvature. Okay? So what we're looking for here is determine the x and y components of the force exerted by the jet and its direction and velocity as it leaves the vein. So this is our x and y components, x and y. So we will have here Fy and then this is the Fx. So given the jet diameter with the diameter of 50 mm and the velocity of the jet is 15 meter per second. A jet having a velocity of 15 meter per second is deflected by a vein. So meaning it's the initial velocity, because this is the velocity of the jet that is being deflected by the vein. So V1 is equal to 15 meter per second. And then the vein, as mentioned a while ago, is 6 meter per second. So V prime is equal to 6 meter per second. In the same direction as the jet. So find the values of x and y. So we're going to use the formula f of x is equal to rho q. Of course, this is moving already, signifying the v prime having its value. So let's put here q prime. This is the case number 2. And v1x minus v2y. Then we have Fy is equal to rho Q prime, then V1y minus V2y. Oops, this should be V2x. There. So what are the values that we need? We need the value for Q prime. For Q prime, to get its value, we need the value for U. So remember in our discussion of the formula a while ago, U is the relative velocity of the jet. And then we have the V2. The V2 is the absolute velocity of the jet as it leaves the vein. So this is our U, this is our V sub 2. So our U is equal to initial velocity minus the V prime. So U is equal to 15. V1 minus V prime 6. U is equal to 9 meter per second. Therefore, we can get now the value for Q prime. That is area times the U. That is equal to pi over 4, the actual area of the jet. So jet having the diameter of 50 mm, so that is 0.05 squared. And then the U here is 9 meter per second. So what's the value for Q? shift pi over 4 times 0.05 squared times 9. So 0.018 cubic meter. So 0.018 cubic meter per second. Let's find now the value for V1x, V2x, V1y, and V2y. And it's from the parallelogram that we had. So this is our U. Say this is the U here with the 60 degrees. This is the V2, and this is the V1, the V prime. This is our V prime. So it's based on these three velocities here. So the reason why it looks like a parallelogram, because we will transfer here the U in this side, being there. This is the U, and same U here, and then this is the V prime, and then this is the V sub 2. So this is the V prime. V prime is equal to 6 meters. And then we have here U sub x. And then this is V2x. And then as for the V2y, since this is upward for the V2, it is upward and it is opposite our Fy, we're going to put here negative V2y. So here, our V1x is easily equal to V1 is equal to 15 meter per second. For V2x, that is equal to V prime plus Ux, and that is equal to V prime being 6 plus Ux being the U, the value of U is 9 cosine theta. Our theta here is, so theta is 60 degrees. So that is cosine 60. So V2x now is equal to 6 plus 9 cosine 60. That is 10.5. 10.5 meter per second. Now V1y is equal to, so there is no y component for V1. So V1y is equal to 0. V2y, however, is equal to the negative U sine 60. And that is equal to 9, or that is negative 9 sine 60. So V2y is equal to 7.794. So negative 7.79. That is in meter per second. So we can now substitute all these for f of x. So that density is equal to 1000 times the q prime is 0.018 times v1x is 15 minus the v2x. v2x is 10.5. So f of x is equal to 1,000 times 0.018 times 15 minus 10.5. That is 81 Newton. So 81 Newton. And the direction is to the right. Next, we have the f of y. So f of y is equal to 1,000 times 0.018 times the v1y of 0 minus v2y of negative 7.94. So fy is equal to 142.92. So 142.92 Newton. And the direction of this, since it is positive, therefore this is downward. So this convention positive downward here. So since we got a positive value, therefore it's downward. Okay, so that's example number 2. So it's looking also for the velocity. So the velocity as it leaves the beam. So V2. We forgot the V2. So since we already got the V1, V2x and V2y. So V2 is equal to square root of V2x squared and then V2y squared. So V2x is 10.5 squared plus negative 7.90 9 sine 60. 7.79. I see, it should be 79 here. 79. So 1,000 times 0.018 times 7.79. 140.22. So it should be 140.22. So it should be 7.79 squared. So V2 is now equal to square root of 10.5 squared plus 7.79 squared is 13.07. 13.07 meter per second. Okay, so that's example number 2. Next, we'll have example number 3. A jet issued at the rate of 155 liter per second and a velocity of 35 meter per second strikes a blade moving in the same direction at 20 meter per second. The deflection angle of the blade is 150 degrees. Neglecting friction in the blade, determine the x and y components of the force exerted by the jet on the blade. So we have a deflected vane 150 degrees. So this is the 150 degrees deflected vane. Therefore, it forms an acute angle for our water here. And that is 30 degrees. So a jet is issued at the rate of 155 liter per second. So that is Q. That is Q. So a jet is entering at Q is equal to 155 liter per second, and that is 0.155 cubic meter per second. Then the velocity, a jet issued at the rate of and a velocity of 35 meter per second strikes a blade. So that means this velocity happened before striking the blade. So we have here initial velocity. So it's the initial velocity V1, 35 meter per second. And the blade is moving. So this blade is moving V prime. So we have our V prime equals 20 meter per second in the same direction as the jet. So it means that direction here is the direction upon entrance of the blade, and not this. You're not going to put this V prime in this direction because it's not following the direction that is going out of the vein, but rather it follows the direction as the water enters the vein or the blade. So the deflection angle is 150. Determine the x and y components of the force. So this is our x and y component. Obviously, this is our f of x. The water is striking the blade to the right direction. And we have to put here Fy downward. So it means when we get a positive value, this assumption is correct. But if not, then it's in the opposite direction. Okay, so the force exerted by the blade. So again, we're going to use the formula for the case 2. So in order to use the formula for case 2, we need the value for the u. Okay, so here is the u here. This is our u. U being the relative velocity of the jet. As you can see, it follows the direction of the jet as it leaves the vein. So this is u. And then our V2 is, we are going to assume for the V2 because it's either the direction of V2 is like this or it could be like that. So the only way to find out is to solve for the value of u first. So we have here u again is equal to v1 minus the v prime because they have the same direction. So you can get the clue here that in order to perform this operation, you have to make sure that v1 and v prime have they're both in horizontal. I mean they should be in horizontal direction. This is the vx direction. That is equal to 35 minus 20. So u here is equal to 15 meter per second. Now we don't have diameter of the jet, so it's missing the problem, the diameter of the jet. But we can solve it using the given q. So from the given q there, that is q1 is equal to the area and then the initial velocity. So 0.155 is equal to the area of the jet times the v1, that is 35. So area now is equal to 0.155 divided by 35, that is 0.0044. So 0.0044 meters square meters. Then we have now our Q prime is equal to area times U. So Q prime is equal to 0.0044 times the U, which is 15. So we now have the value for Q prime. 0.0044 times 15. So that is 0.066. So 0.066 cubic meter per second. Okay, now let's go to the assumption. Now if we assume that the if we assume that the V2, let's use a different color. If we assume that V2 is like this, let's see if the assumption is correct. So U, this is V prime, and this is the inclination of V2 is greater than U. So there. Let's see. So we're going to form again a parallelogram. So let's exaggerate this a bit in order to get the values. There. So this is 150 degrees, therefore this one here. So this is 150 degrees from the horizontal up to where? The direction of the U. So 150 horizontal up to the inclination of U. So this now here is the 30 degrees. This is our 30 degrees. This is U of 15. This is the 35. So V1. Let's just see it like that. So this is also same, so parallel. This is V2 and then this is V2 as well. Let's see if this assumption is correct. Okay, so this is our V1 of 35. Then this is our V2x here, and this is our UX. So what's the value for UX? UX is equal to 15 cosine of 30. So what is 15 cosine 30? That is 12.99, or that is 13. So UX is 13, and you can observe that this U sub X is less than the 35, being the 35 there. Therefore, this assumption is incorrect. So that means the direction of B2 there is also incorrect. So we will now move this in the correct direction. Therefore, our V2 is actually in this direction. So really, is it really here? in this direction. So we can again test V2. So having the U here in 30 degrees, we have our V2 here. We have our V1. So what will happen? So again, we will form a parallelogram. So this is now the U. There goes the broken line. This is the U here. And the angle to the horizontal is 30 degrees. And the angle here is same, that is 30 degrees as well. Then this is our V2. And here, our U here is same as this one here. This is also U. Therefore, so we now have here V2x. This is our UX, and this is actually the V1 of 35 meter per second. Oh no, the V1. Why do I keep saying it's the V1? It's the 20. Oh, by the way, what we did a while ago, it should be the 20 meter per second. Still, the UX is equal to 13 is less than the 20 degrees at 20 meter per second, right? So still, the assumption previously is incorrect. So we should have been using the 20 meter per second a while ago. So we're focusing this into our parallelogram. So as for the V2y, that will be negative since our downward here is presented as positive. So we have here negative V2y. Okay, so I think our representation here is complete. Now let's find here V1. So V1x, let's give some room for the components. So V1x is equal to this one here. That is V1 equals 35 meter per second. How about V1y? For V1y, that is equal to 0. Now for V2x, so V2x is equal to, that is 20 minus the u sub x. So 20 minus u sub x is equal to 20 minus the u, which is the, what's the value of u again? It is 15. So that is 15 cosine of 30. So 15 cosine of 30, that is 12.99. So V2x now is equal to 7 7.01 meter per second. Next, our V2y is equal to the uy, that is 15 or negative. This is negative 15 sine of 30. So V2y is 15 sine 30. Oops. This is 7.5. It's negative 7.5 meter per second. Now substitute all of this to our formula. F of x is equal to rho q prime b1x minus b2x, that is 1000. Q prime is 0.066 times b1x is 35 minus b2x 7.01. So f of x is now equal to 1000 times 0.066 times 35 minus 7.01. So 1847.34. F of x is 1847.34 Newton. And the direction here, since it's positive, the direction here is to the right. Next, we have our Fy is rho q gamma b1y minus b2y. So that is equal to 1000 times 0.066 times b1y is 0 minus negative 7.5. So Fy is now equal to times 7.5, 495 Newton. So 495 Newton, positive, therefore it is downward. So that's for example number 3. The x and y components exerted by the jet into the blade. Now let's go to the last example. A nozzle discharges 50 liter per second with a velocity of 15 meter per second. So the Q here is 50 or 0.05 and the velocity V1 is 15 meter per second. The nozzle is inclined downward such that the jet strikes a fixed curved vane. The nozzle is inclined downward such that as the jet strikes a fixed curved vane, it is directed 30 degrees down from the horizontal. The jet is deflected upwards with the horizontal as it leaves the vane. Determine the x and y components of the force exerted by the jet on the vane. So that means the nozzle is inclined downward. So the nozzle or the origin of the jet is directed downward. So it's like this. So this is our horizontal. So our jet enters the curved vane 30 degrees down from the horizontal, and then the jet is deflected upwards 60 degrees with the horizontal as it leaves the vane. So meaning that as it enters 30 degrees, it leaves 60 degrees. So meaning it's deflected in such a way that it is 60 degrees with the horizontal. So something like that. So this is our 60 degrees. So that means water enters 30, leaves 60. Okay? Not it's not like this. So it's not entering 30, leaving 60. So it doesn't make sense, isn't it? If it does it like that. Because if you think that the deflection is in this direction, so it's too steep for the water to go back like that. So like that. So possibly it's talking about the deflection of the water like that. Okay, so let's have a better drawing on that. So there you go. There goes our water, leaving 60 degrees but entering 30 degrees. Then the nozzle discharge is Q. So Q is equal to 0.05 cubic meter per second. And the velocity is 15. Now, the velocity is not horizontal here. Rather, it follows the angle of the entrance of the jet. So that will be 30 degrees with the horizontal as well. So it enters 30 degrees. V1 equals 15 meter per second. And it leaves 60 degrees. Now, the problem did mention that the vane is fixed. So what happens when the vane V prime here is 0? That means our V2 is equal to V1. When V prime is 0. So what are we looking for here? Determine the x and y components of the force exerted by the jet on the vane. So x and y components, so we have our force as directed to the right, positive, and the force directed downward as positive. So this is Fy, this is F of x. So this is case 1. Case 1 wherein the vane is not moving. So V1x, so V1x here is simply 15 cosine 30. That is 15 cosine 30 of 12.99 meter per second. V2x is equal to, that is 15, still 15, but this is cosine 60. That is 7.5 meter per second. Then we have now the formula for f of x, or so let's complete it first. V1y. How about V1y? That is 15 sine 30. And the direction here is downward for Fy. So we will take that as positive. So 15 sine 30. 7.5. So for V1y is 7.5 as well. And then V2x is equal to 15. Also, it's directed upward. So that this is negative 15 sine 60. So that is equal to negative 12.99 meter per second. Substitute all of this into the formulas. So f of x is equal to q gamma over g. This is the other formula. The other formula here, the second one. So do not be confused here. Then this is V1x, still the V1x minus V2x. So that is equal to Q of 0.05 times, what's the gamma for water? That is, if we are going to take the answer in Newton, we'll put here 9810 Newton per cubic meter over the acceleration of gravity. V1x is 12.99 minus V2x 7.5. So what is f of x? 0.05 times 9810 over 9.81 times 12.99 minus 7.5. So we have 274.5 Newton. 274.5 Newton. And the direction there is to the right. Next, we have Fy equals Q gamma over G V1y minus V2y. That is equal to 0.05 times 9810 all over 9.81 times V2x. This is V2y. So V1y is 7.5 minus the V2y of negative 12.99. So Fy is equal to, that will be 7.5 minus negative 12.99. So 1024.5. So 1024.5 Newton. Since this is positive, therefore it is downward. Okay, so that's for example number 4. Okay, so that's all for this video.